Have you ever wondered how companies predict future sales, or how scientists forecast climate changes? At the heart of many such predictions lies a surprisingly simple yet powerful statistical tool: linear regression. It's a fundamental machine learning algorithm used to model the relationship between a dependent variable and one or more independent variables by fitting a linear equation to observed data. Essentially, we're trying to predict a continuous value. The core idea is straightforward. Imagine you have a collection of data points, perhaps showing how a student's study hours relate to their exam scores. Linear regression tries to find the best possible straight line that describes this relationship. This line then allows us to make predictions for new data points. For example, if a student studies for a certain number of hours, what score can we expect them to achieve? Visually, this involves plotting your data on a scatter graph. Let's say we plot study hours on the x-axis and exam scores on the y-axis. Each student represents a single point on this graph. Once all points are plotted, we try to draw a single straight line that passes through, or as close as possible to, the majority of these points. This line is often referred to as the line of best fit. Mathematically, this line of best fit is represented by a simple equation: y equals beta plus beta x plus epsilon. Here, y is the dependent variable we're trying to predict, like exam scores. X is our independent variable, such as study hours. Beta is the y-intercept, the value of y when x is 0. Beta is the slope of the line, telling us how much y changes for every 1 unit change in x. The epsilon represents the error term, acknowledging that our predictions won't always be perfect. So, how do we find this best line? It's all about minimizing the error. For every data point, there's a vertical distance between the actual observed y value and the y value predicted by our line. This distance is called a residual, or error. Our goal is to find the line that makes these residuals as small as possible, on average, across all our data points. The most common method for achieving this is called ordinary least squares, or OLS. Instead of simply summing the errors, which could cancel out positive and negative values, OLS squares each residual and then sums them up. By minimizing this sum of squared residuals, we penalize larger errors more heavily and arrive at a unique line that is considered the best fit for our data. While powerful, linear regression comes with several key assumptions. First, there's the assumption of linearity. The relationship between your independent and dependent variables must genuinely be linear. If the relationship is curved, a straight line simply won't be an accurate model. Second, we assume the independence of errors, meaning the prediction error for one data point does not influence the error for another data point. Continuing with assumptions, we also have homoscedasticity, which means the variance of the errors should be constant across all levels of the independent variable. In simpler terms, the spread of our data points around the regression line should be roughly the same along the entire length of the line. Finally, we assume the errors are normally distributed, particularly for making reliable statistical inferences and confidence intervals. Let's consider a practical, real-world example: predicting the selling price of a house based on its size. Here, the house price is our dependent variable, and the house size in square feet is our independent variable. We collect data from many recent house sales, recording both their size and their final selling price. We would then plot this data on a scatter plot. As we'd expect, we'd likely see a general trend where larger houses tend to have higher prices. Linear regression would then calculate the coefficients for our equation, beta and beta, drawing the line of best fit through these data points. This line visually represents the average relationship between house size and price. Once we have our regression equation, we can interpret the results. The beta might represent a base price for a house even with 0 square feet, though this often isn't meaningful in a real-world context for x equals 0. More importantly, the beta tells us the average increase in house price for every additional square foot of living space. For example, if beta is 100, it suggests that, on average, each additional square foot adds $100 to the house's selling price. In summary, Linear regression demystifies the process of predicting continuous values by finding a simple straight line that best represents the relationship between variables. By understanding its assumptions and the method of fitting this line through ordinary least squares, you gain a powerful tool for making data-driven predictions in countless real-world scenarios, from economics to environmental science. It's a foundational concept that paves the way for understanding more complex predictive models.